welcome all of you to this session of heat transfer. I am Arindam Mukherjee, Assistant Professor of Automobile Engineering Department. In the previous lecture, we had discussed about the one-dimensional general heat conduction equation. Actually, we had derived this equation for all the three dimensions and all the time frame. Okay, so it was the equation which can be applied for the space coordinates along with the time coordinates. So the general heat transfer equation, the general conduction heat transfer equation helps us to provide to find a general temperature distribution inside a control volume with respect to a certain time and certain space coordinates. But we had also discussed the boundary conditions. That means to find the proper solution of a certain heat transfer problem, we need to apply those boundary conditions. And now today we'll be applying this uh, general heat conduction equation for the uh, rectangular slab. We will consider a rectangular slab and we'll consider a heat transfer there. So let us move on to that. Before moving on to that part, I would like to mention that we'll be applying this one-dimensional heat conduction equation for three specific objects or three specific geometries. That is the plane walls, the cylindrical surfaces, and the spherical surfaces. So today we will be starting this derivation from the plane walls. So we'll consider a case where we will be applying the general heat conduction equation, where we'll uh, necessarily take some primitive assumptions. The assumptions are as follows. So it is one dimensional heat conduction. It is steady flow. The material is isotropic and homogeneous throughout its entire mass, and there is no thermal energy generation within the control volume. Okay, so with these primitive assumptions, we will start to analyze the one-dimensional heat conduction in a plane wall. Okay, so let us move on to that. So let us consider one-dimensional heat conduction case for a plane wall. So this is your plane wall, which is shaded in a light yellow color, and you can see that the the boundaries of the plane walls on the left side and the right side, they are maintained at the constant temperatures T1 and T2. Since T1 is greater than T2, by virtue of this temperature difference, heat transfer will start within this plane wall. Okay, now this these two lateral surfaces, they have been insulated, so there is no heat transfer in this direction. Okay, the only direction of heat transfer is in the horizontal x direction. So we have assumed that this plane wall has a thickness of delta. uh, it has an it has a thermal conductivity K, which is constant. That means we have already assumed that material is isotropic and homogeneous, so this thermal conductivity is not going to change for all over the surface. So let us take a certain area. So let us take a strip of this plane wall whose thickness is dx, and within this region the temperature difference is dt. So let us consider this temperature difference as dt. Okay, now you would be interested to find out the temperature and distance relationship. That means the spatial and the would be like to interested to find out the spatial distribution of temperature. That means how does temperature changes along with this space coordinates. So here there is only one dimension, so the temperature distribution would be only a function of T, will be a function of x. Okay, and since there is steady state heat conduction going on, that means it is not a function of time. As you know, in case of steady state, there is the thermodynamic properties remain invariant. Okay, so let us start with the derivation part. Let us observe how this one dimensional heat conduction general equation can be applied for this case, and what are the final solutions. So ultimately our objective is to find out the temperature distribution at any point within this wall and the rate of heat transfer at which the heat is flowing here. Okay, so this is these two are the primary objectives. So we will move on to the solution part. So let us see how this solution can be done. So from our discussions on this one conduction general equation, it is quite obvious that you are quite well known about this equation. Now if we apply this case for one dimension, then this Laplacian operator can be changed to it will be only a function of x. So ultimately we will be left with this d2t and dx2 factor. So the change of temperature, the second order of change of temperature, or the change of temperature gradient with respect to the y coordinates and the z coordinates will be zero, since heat is transferring is since the heat which is transferring is in only the single direction, and that is the direction x. And whenever we are considering the steady state, that means the temperature, which is an property of the system, it remains invariant. That means this dt becomes 0, and without any thermal energy generation, this qg is 0. So this equation, which was so large here, it just reduces to a simple equation like this. Now what we'll do, we will perform is simple integration here. So it will be like this, ddx of, we can express this d2t dx2 as like this. You know, from your basic understandings of calculus, it is very simple that we are explaining this. Okay, so if we explain or express this one as like this, then if we perform integration on both the sides, then it is obvious that we will end up with this result. Okay, so dt dx, after integration, dt dx becomes equal to c1, which is obviously an integration constant. Now let us see if we perform the integration once again. So it will be dt, so it will be dt equal to c1 into dx. So we are interested to do the integration once again. So here we are not taking any kind of limits, because we will solve this equation with the help of boundary conditions. We will apply the boundary conditions and then we will find the temperature distribution within this certain space. So it will be c1 into x. It is very simple integration, you know these things very well. So after the performance of this integration, the result becomes like this. So this is your c1. Just give me some time, I will write it in a better way. So this is your c1x plus c2. Now we will apply the boundary conditions. So let us consider this point. So this point indicates that x is equal to 0. Now what is the temperature? So you know this whole phase is maintained at temperature T1. So at x equal to 0, this temperature T will be T1. And at x equal to this point, now what is the coordinate of this point? It is the thickness of this wall, which is taken as delta. So x equal to delta, what will be the temperature? Can you guess? So it is very simple, right? So it will be T equal to T2, because because x equal to delta represents this phase, and you know we have assumed that this phase is maintained at a constant temperature T2. So x equal to delta, T becomes T2. Now if we put this value x equal to 0, if we put this value x equal to 0, then it is quite easily understood that we will get the value of this constant C2 as T1. And after we put this x equal to delta 1, then we will get C1 into lambda, delta, plus T1. So you can easily find out the value of C1, which is nothing but T2 minus T1 by delta. Okay, so if C1 is equal to T2 minus T1 by delta, then you can write the whole temperature distribution now. So T can be written as T2 minus T1 um, into x plus T1. So now you can understand that the function which we have just now derived, this is the temperature distribution along this plane wall. So if you put the value of x, you can find out the temperature of this within this plane wall. Okay, now uh, this line was already there when we started the derivation. So I think some of you may have a question, how did this line emerge? Okay, how this line can be generated? Okay, so this is because of this equation. You can easily understand that this equation resembles to the straight line equation of y is equal to mx plus c. This m is your this one. Okay, so this is quite simple to understand that this is nothing but a equation of straight line. So we get a straight line here. Okay, so now we have derived the temperature distribution within a plane wall. So after we have performed this derivation, now let us see what is the rate of heat transfer within this. What is the rate of heat transfer which is going on here? So till now we have taken the heat transfer. Let us take Q dot as the rate of heat transfer. Okay. So this Q dot. So now we are interested to find out the value of this Q dot. That means the heat transfer rate. So before doing the derivation, or before doing the calculations for this Q dot, I would like to say you another thing regarding this temperature distribution. So if you just arrange this equation like this, uh, T minus T1, so this T1 comes here, this T2 minus T1 is divided, and you get a function like this. So this is what we call a dimensionless parameters. You can see uh, this one has a unit of temperature and this one too. So this is nothing but mm, a dimensionless function of this temperature distribution. Okay, so now let us move on to find the heat transfer rate. Now according to Fourier's law, you know that According to Fourier's law, according to Fourier's law, you know that heat flux is proportional to the negative temperature gradient. Okay, that means Q double prime is equal to minus K into dt dx. Since the material is isotropic and homogeneous throughout its mass, we have taken this constant thermal conductivity. Okay, now if we want to find out the heat transfer rate, then we need to multiply this heat flux by the area. So the area of heat transfer is the normal is in the normal direction of the heat transfer direction, right? So we are concerned about this area. Okay, so just let us write K. We have considered, or we have taken this area as A. Okay, so we are providing this value Q A dt dx. Now this is very simple. If you perform the derivative of this temperature distribution model, which we have just now derived, we will find that if we derive this dt dx, then we'll get what? We'll get this function only. So it will be t2 minus t1 by lambda, or in other words, just rearranging the terms, we'll get t1 minus t2 by lambda. Okay, so I'm sorry, it was delta. So we have found out the temperature distribution and the heat transfer rate. Now this heat transfer rate can be found out in an alternative way. I will show you after a few minutes. So before that, I would like to revise the things which I have said. So this is your temperature distribution and this is your heat transfer, which is going on through the plane wall. Okay, so this is your temperature distribution. That means if you put the value of x, if you want to find out the temperature at a certain location, then you need to know this x. You just put out this value of x. If you know these boundary temperatures, then you can easily find out this temperature. Okay, it is as simple as this. So now let us see the alternative way to find out the heat transfer rate. Okay, so this is also an application of Fourier's law. So we know that. So I'm not going to say the Fourier's law once again. I will write it again here. So Q is equal to minus K dt dx, right? Or we can write this Q into dx is equal to minus K A into dt, right? So if we perform integration for the variables dx and d theta, so in the previous case we have taken this thickness of this wall as a delta, so that means we'll integrate this over the range of 0 to delta, and the temperature limits will be the boundary temperature at the left side, which is T1, and the boundary temperature at the right side, which is T2. Okay, so after integrating and putting the values, it is a very simple integration. You can see that you will get this one, right? Minus K A T2 minus T1. Okay, I'm sorry, the limits would be delta here, because I have taken the limits of 0 to delta, but mistakenly I have written down x here. So this Q will be equal to K A T1 minus T2. So I am just writing in all positive terms here. So Q is equal to Ka T1 minus T2 by delta. So which is exactly same as the previous one. Okay. So this heat transfer can be derived in this way also. So this is an alternative way. So now we have uh, known to find out the temperature distribution along with the heat transfer through the. So we can see that this heat transfer rate through this plane wall for one-dimensional heat conduction can be formulated by this way. Now let us see how this formula can be analogous to the electric energy transfer. So let us see that. So here comes your analogy. So just so this heat transfer rate is equal to Ka T1 minus T2 divided by delta. Okay, now this can be written in this format. So T1 minus T2 divided by delta. Now, if you consider the Ohm's law, you know that electricity uh, or current, which we say, is the can be represented by this also. Okay, now if you just equate these two equations, if you try to find out the similarities between these two equations, you will understand that this is a flow quantity. Heat flows through the surface. Okay, now this is the reason. So this temperature difference is the reason because of which heat flows. Now here you'll see this voltage difference is the reason. This is why this electricity flow. Then you can obviously understand that this resistance will be equated to this resistance. So you can write this R equal to delta by Kaa. Now this R is defined as thermal resistance. Okay, so this is the electrical analogy which we would like to mention. Now according to the condition where we had taken a plane wall and the heat transfer was defined by the straight line like this, and the heat transfer was Q, so the plane wall had a thickness of delta. So for this condition we can draw a electrical circuit which would represent the heat transfer cases, but with the help of a certain circuit. So let us see how we can do that. So this is your circuit. This is the thermal resistance I am talking about. So T1 and T2 are the temperatures at the endpoints, and T, because of the temperature difference between T1 and T2, this heat Q flows. Okay, so this thermal resistance will be denoted by this formula. So the distance, the thickness divided by the multiplication of thermal conductivity into Ka, that is thermal conductivity into area. Okay, so this is the concept of uh, electrical analogy or thermal resistance. So if you find that there is another one here which has a certain temperature T3, then we can draw another one circuit which will be having a thermal resistance of RTH2, and if this thickness is let us say delta 1 and the material is different from this, if we take K1 as the thermal conductivity of this material, and the area as A1. Then we can write this RTH2 as delta 1 divided by K1 A1. Okay, so by virtue of this, we can easily create the thermal resistance formulas for different cases. So this can be applied for convection also. Now you must know that according to the Newton's law of cooling, we had discussed about this. So this convection, um, so this was convection, can be written by the help of this formula. Okay, so you can write this Q convection as, you can also write this Q convection as T minus T infinite divided by 1 by H. So this is your convective thermal resistance, and the previous one which I had shown you, it would be called as conductive thermal resistance. Okay, the circuit would be similar. So T and T infinite, that is the ambient temperature. Obviously, because of the temperature difference in T and T infinite, this is the heat transfer Q, and you can see uh, um, you will see RTH. So let us see, RTH convection is a thermal resistance which can be written as RTH convection can be written as 1 by HA. So this is your convective thermal resistance. So now it is quite well understood that we can form any kind of electrical circuits for a heat transfer or specifically a conduction problem for a single plane wall or a composite plane wall. So we'll try to apply this electrical analogy concept for the composite plane wall, and we will observe how we can derive this type of formula. So with the understanding of electrical analogy concept, let us introduce the concept of conduction through composite wall. Now what is a composite wall? A composite wall is nothing but a combination of several heterogeneous layers. Okay, like we can take the example of our house, where you can find that for both the sides a layer of insulation is provided to the either side of the bricks. So examples of these composite walls can be for the boiler walls, for the furnaces, and for most of the heat exchanger devices. You will find that this kind of composite walls are used. So we will solve this heat transfer problem for this composite wall with the help of the basic understanding of electrical circuits. Okay, so just in a few moments earlier we have discussed about the electrical analogy concept, and we will see how this concept can be used to derive the equations or the temperature and the heat transfer calculations for this composite wall. So just give me some time and I will draw the electrical circuit for you, and therefore I will explain it. So you can see the electrical circuit. That means we have applied the concept of electrical analogy with the heat transfer problems to generate this circuit. Now this is the flow quantity. That means Q amount of heat is flowing through all of the walls. Okay, so there is no change in the quantity of the heat. Okay, the heat which is flowing through these component walls, they are not going to change, so this Q remains unchanged. That is quite easy to understand. So this means that we'll have a circuit which will be of series type, That means it will connect in a linear format of all the resistances. So this is your voltage differences. Exactly. So this is your differences by the virtue of which heat flows. So here you can see T2 is the temperature of this interface, T3 is the interface temperature of here. So since for this wall whose two sides are maintained at a temperature T1 and T2, heat will it will be obviously resisted, and the thermal resistance is given by RTH1. Again, for this wall, for the wall B, heat will be resisted, and the temperatures at which the boundaries of this wall are maintained is a T2 and T3. Okay, and for the last one, for the wall number, so for the wall number B, you can see this RTH2, this is your thermal resistance, and for the wall number 3 or wall number C, this RTH3 is the thermal resistance. Now you can see this is the thicknesses of the three different walls. So from the concept of heat transfer in plane walls, we know that this equation is valid. It was K A T1 minus T2 T1 minus T2 divided by the thickness of the walls, right? So if we remember this equation, then for this wall A, we can write this quantity as K. So let us assume that both these three walls have the same area. So we are not going into complications here. We are taking these three walls have the same area. Obviously, they don't have the same area, but we are considering it. Okay, so it will be T1 minus T2 divided by del x A. So this is your thickness for the wall number A. Again, for wall number B, we can write this equation, but in a little different form. It will be like this: K into A, but the temperature difference would obviously change. It will be what? It will be T2 minus T3, and divided by the thickness, it will be del x B, right? And for the wall number C, this equation can be modified like this: K into A into, it will be, so sorry, just I have to use a different ink here. So it will be K A T3 minus T4 divided by del x C, because this is the thickness for this wall number C. So now we have found out the heat transferring through these three different walls. Now if we change this heat transfer equation into the format of resistance equation or the Ohm's law of resistance, then it is quite obvious that we'll find this kind of equation. So it will be like this: it will be like K into E, right? For this one, we will see that this equation can be changed into del x B divided by K, and this one will be also Ka. So just help me. Okay, I have removed these three, and now we can see this heat transfer can be found analogous to the electricity transfer equation, that is the Ohm's law of resistance. And now you can understand that this thing, this RTH1, this is the thermal resistance which is observed by this heat while transferring through this wall, and this can be written as del x, it can be written as del x A divided by Ka. Okay, again we can write RTH2 equal to del x b, I'm sorry, so it will be del x b divided by ka. Okay, it is very simple, so it will be del x b by ka, and this thermal resistance for the wall 3 will be del x c divided by ka. So this is simple algebra here. Okay, so now if we are willing to find out the heat transfer in terms of the uh, boundary temperatures, okay, the one surface, the left surface of this composite wall is maintained at a temperature T1, and the rightmost surface of this composite wall is maintained at a temperature T4. So how we can find the rate of heat transfer in terms of this leftmost temperature T1 and rightmost temperature T4? So we can simply write that Q is equal to the difference of temperature by the sum of thermal resistance. Okay, so it will be written as so just so we can write sum of thermal resistances. Okay, so this represents the sum of all the thermal resistances which have been observed by this heat while transferring through these different walls. So it will be something like this: T1 minus T4 divided by R1 plus R2 plus R3. Remember that this R1 represent this RTH1, which is the thermal resistance for the wall A, R2 is the thermal resistance for the wall B, and R3 is the thermal resistance for the wall C. So by uh, virtue of this formula, we can calculate any the heat transfer for any number of walls. So now let us if you find that there are n number of walls, then what would you do? How you can write this equation? You will simply write T1 minus, so it will be T1 minus T n plus 1 divided by summation of delta R TH n is equal to 1 to n. Okay, so I hope that now you can calculate the heat transfer for the composite wall surfaces. So if you know the number of composite walls, then you can easily calculate the heat transfer rate. Okay, so by the concept of these electrical circuits, you can derive the heat transfer rate for any kind of composite walls. Okay, so with that, we'll end this discussion on the composite plane walls, and we will move on to a different case where we will see that if there is heat transfer going on between the system and the surroundings. Okay, and the system is represented as a plane one. So here, okay, we have actually we have already discussed about the concept of electrical analogy, so let us not carry forward it. So this was a simple type of discussions. Now here, so this is our motif. So here you can see this is your solid surface, this is the wall surface through which the heat is flowing. This Q is obviously taken as the heat flux. Okay, and this side of this wall is interacting with the certain fluid. Okay, so let us assume that a certain fluid is flowing in this direction. So now our objective is to calculate the heat transfer equation for specifically this kind of cases. So we have to find out the relationship between the heat transfer by convection as well as the heat transfer by conduction. Now I hope that you are getting my words, because you know that from the basic understanding of convection, that whenever you will see that there is a solid surface and there is a fluid motion going on between these two surfaces, between the fluid and the solid, so it is quite obvious that heat will be transferred via the mode of convection if the fluid is in motion. Okay, so depending on the temperature differences between the solid surface and the fluid, the heat transfer direction may vary, but our objective is to find out a relationship between the convection heat transferred and the conduction heat transferred. Okay, so let us explain this case. So in case of convection, so we would like to start with the basic understanding of convection. In the previous class I have discussed about this convection concept in a very short manner. Let us take this here. So let us write this T minus T surroundings. Okay, so here you can see this H is the convection heat transfer coefficient, A is the area of heat transfer, and this is the temperature difference. Okay, now you can see heat transfer is going on between this side of this plane wall and this one. Okay, so here you can see the temperature of this fluid is maintained at the temperature T infinite. Okay, so for this case you can write this convection equation. So obviously this T will change into T2. Now the heat it is uh, at which it is flowing through the walls, and it is also flowing and it is also interacting with the fluid. Since the magnitude of the heat doesn't change, we can write this equation like this also. So this is because of the mode of conduction, and this is for the convection which is taking place here. Okay, so this is a case where conduction and convection, they are taking place combinedly. Okay, so we have to consider both the formulas of conduction as well as convection. So in the diagram the thickness of the wall is not given here, so let us take delta as our thickness of the wall. So this is Q conduction will be equal to Q convection. Okay, that means if we write this as a general term, in a general term Q, then we can say this Q is equal to HA T2 minus T infinite, as well as Q equal to KA T1 minus T2 by delta. Okay, so in the format of thermal resistance or the electrical analogy, we can write these equations in this format also. So we'll be writing this equation. So this is for convection, right? And this is for conduction, which we have discussed a lot of times. So we have already discussed the concept of thermal resistance in composite walls. So this can be found out. So this is your delta. Okay, so if you want to find out this heat transfer in terms of temperature T1 and this final temperature, then what will be the equation? It is simple again. So T1 minus T infinite and the summation of thermal resistances. So here there are basically two heat resistances present here. One is because of the conduction heat transfer, and another one is because of the convection. So T1 minus t infinite divided by 1 HA plus delta by KA. Okay, so if this surface starts to interact with a certain surrounding which is maintained at the temperature TA, then we have to consider this conduction also, this convection also. Okay, so this can be also implicated here by adding up the thermal resistance because of this convection heat transfer. So with this understanding, when we see that there is a case where combined heat transfer and conduction is taking place, at that cases we can understand that if we find the temperature at which the one side of this wall is maintained and the another side at which is the final temperature after the convection is taking place, so just get the difference of these two temperatures and divide it by the sum of thermal resistance. Now heat is being resisted because of the two modes, the conduction and convection. So you need to add up the thermal resistances because of this conduction as well as convection. So if you add it up, then you will find the rate of heat transfer. Okay, so this is not any problem, I believe. So with this understanding of the combined conduction and convection problem, let us take some problem. Oh, I think today we shall not take any problems because we have discussed the theoretical part in a detailed manner. I think today, if I discuss the numerical problems, it will be creating a lot of pressure on you guys. So, I think I should end my lecture here, and I hope that you have understood the theoretical part in a proper, detailed way so that we can discuss the problems next day. Okay, so I would like to end my lecture here and goodbye. See you on the next lecture. So till then, goodbye.